Hello. Okay, so this is another rewrite story that it went so well that I want to share with everybody. Just like many talks, I'm going to be touching upon a lot of things. I'm not going to deep dive on any. I just want to give you as much exposure as I can to things and tools and techniques that I found very helpful when writing my first Go production service. So to give you some background, last year I was working at Fog Creek Software out of New York. If you guys have heard of us, you might be familiar with Kiwi. This is the Fogbug's mascot. I was working on Kiln. Kiln is Fog Creek's Git and Mercurial source code hosting service. It's like a GitHub that works with Git and Mercurial. Before I worked there, I hadn't heard of Mercurial. I'm very familiar with it now. Most of my work was in C# and Python. I tried to gravitate more towards the backend stuff. And also last year, I was lucky to attend Google I/O. And I went there having no idea what Go was. I actually had never heard of it. And now everywhere you look, it's everywhere. I don't have to explain to you why I fell in love with it so quickly. I went to every one of the Go talks I could. I met some of the Go authors, and it was awesome. So I knew that I had a solution to a problem that might come up someday. So I needed to ship something awesome in Go. I wanted to, there's hobbies, there's fun things I could do in my spare time, but I wanted to prove something at work. I wanted to, use Go to make something awesome for Kiln and to make Kiln better. So I looked around for something to rewrite. There's always something you can rewrite. And I settled on our SSH reverse proxy. Now, I also didn't know what a reverse proxy was when I started working there. So to give you some background on what this is, so when you're dealing with Git or Mercurial, there's two ways to interact with a remote server. There's HTTP and SSH. SSH uses public-private keys. It's more secure. And so if you're going to be cloning a repository from Kiln, and you're using SSH, you're going to be talking to Kiln Proxy. So you're one of those people on the left there. Now, when you talk to Kiln Proxy has to make sure that you are who you say you are by authenticating with your keys, with your key. And then it looks up to see where your data is actually stored. We have lots of backend servers, so it finds out which one is yours, where your repository sits. And then it opens up a connection to the backend server. It has a connection to you. And then all it has to do at this point is proxy all the communication back and forth. So why would I rewrite this? It was working. Well, at the time, our SSH clones were a lot slower than HTTP, and this really shouldn't be. If anything, it feels like SSH should be faster. And also, we had some stability issues, and because of this, our system administrators decided to just restart the service every day. Now, you can imagine if you have a giant repository and you're trying to clone it, you're 20 minutes into a clone, and then it's time for us to restart the whole server. You've just lost everything. You have to start over. It's not cool. So this actually turned out to be a perfect project for Go because there's tons of concurrency. And to give you an idea of this, when you first connect, we're listening on a loop. We kick off a goroutine. That goroutine is responsible for authenticating your public and private key, or your private key. It then connects to the backend server, and once it's got that connection, it then proxies standard in, standard out, and standard error, each on their own goroutine. So, how'd it go? I mean, it went well. So way better than I could have imagined. I just wanted to get it to work, and things went very well. Let me show you how well they went. So this is every few minutes or so we would clone a small repository, and we would keep track of the timing. And this right here is when we transitioned from our Python implementation to Go. And I'll let you guess where it is. I mean, it's a little bit past the pink mark there. So this is just at the launch of the rewrite. At this point now, SSH and HTTP have parity. Now you can see before, this was like a 1 megabyte repository, but before it was taking about 1.5 seconds. Afterwards, it was down to like 0.75. It was almost exactly twice as fast as before. And this does scale up as the repository gets bigger. So we saw some pretty good gains here. And also you can notice that there's a lot less noise also. So what we have is a faster, more reliable, less noisy service. So being my first Go service, I had to figure out how to write a stable service in Go, and I'd like to share some of these tips here. So what are we talking about with resiliency? We're talking about writing a service that doesn't crash, that doesn't have to be restarted every day, doesn't leak memory, and it doesn't hang. Doesn't get stuck. So obviously, this is a big process. There's no magic bullet here. So this is a process that spans development, profiling before launch, and then after launch, monitoring the service. So let's start with error handling. Luckily, not too many speakers have had to say, we should handle every error. I think everyone here understands we should handle every error. I came from Java, where I'm used to very terse code with exceptions that I have no idea if they're thrown or how to handle them. We just don't worry about that in Java. So we've all seen this. This is the pattern. You get a resource, or you get a return value from a function, and it's error, and you don't use an underscore for the error. And then after we check the error, we break out of the function. If there's an error, we defer the cleanup or the close. And one thing I always make sure is to put no new lines in this little block here. As I visually scan code, I want to see that this is one unit that can't be broken apart. And so it looks like here we're handling all the errors, and so we're good. But we know that we should be checking for nil sometimes. So back to our example. What if open resource A can return nil? And what if it's not an error condition? So maybe it's a rare case that we're trying to open the resource, and for some reason it's offline, but this is not an error technically. Well, then our defer statement could panic, right? Well, not necessarily. Of course, we have the technology to avoid this. And one way we can do this is with an inline function, anonymous function. We can just do our little check there, and if it's not nil, then we'll close. The one problem I find with this is that it's gross. I don't like this. Now, can everybody see this? I don't know if that's big enough. So one way I like to handle this is for methods that I know will be deferred. I like terse defers. I like that to be nice and clean. So one thing I actually forgot until recently is that if a method on a struct receives its struct by a pointer, if that struct pointer is nil, that function's still called, and it's passed in a nil for its pointer. And so in this case here, I'm making my deferred statement, the statement that I know will be the cleanup method. I actually check for nil here. And then we get back to our original example where defer resource a.close is actually nil proof. And so I find this to be a good pattern. So let's talk about channels. We all are familiar with channels and how much fun they are. And they are fun, they are awesome, but if you don't know what you're doing, you're going to cause problems. I'm not going to deep dive on this because deep diving on channels would require half a day. But I'd like to reference Dave Cheney's blog post here, which has gotten me through some tough times. It's entitled Channel Axioms. And this is, I mean, literally every time I touch a channel, I just review this. I have it written down somewhere because I want to make sure that I don't misstep with channels. The first three here are the ones I want to focus on, is that if you have a nil channel and you try to write or read from it, it's just going to block forever. And when you block forever on a goroutine, that goroutine never exits. And when a goroutine never exits, it never frees up its resources, and any resources like local variables that it's holding on to. And then when you send to a closed channel, you get a panic. Well, let's talk about panics. So they're usually due, maybe always due, to programmer error. And if you get a panic, it's going to crash your service. Now, I'm going to upset probably half the people in the room and say that I sometimes like to recover from panics. Now, it's a contentious issue. People say, well, it's a programmer error. If you have a programmer error, you should let it crash, or you should fix it. Well, yeah, that's true. But I do make errors, and they do make it to production, and I want to kind of scale back their damage if possible. So without going into the details, you can recover from panics. You should not treat them like exceptions. That's not what I'm doing. So every time when I'm setting up a function, you saw that error block, I make sure that everything I'm setting up will be cleaned up when I leave the function. And so that way, if a panic happens, all those will be fired. So I try to limit areas of the code. I set aside some areas of the code where panics are allowed to happen. I catch it, I do log it, and I do take it very seriously and try to fix those bugs. Let me give you an example. So this SSH proxy was very complicated. And if I'm being honest, I didn't read the full SSH spec beforehand. So we did have one customer who was using a certain build server that was using Git in a certain way that I didn't know about until afterwards. And it was crashing. And we had hundreds of other customers or thousands of other customers that had no problem, didn't have this problem. If I had let this panic creep all the way to production, we would have had a fire, and we would have had outages, and would have had to restart the service over and over. So, in that example, I handle the panic on on the goroutines I mentioned earlier, where you have, which is just handling one client's request. At the high level, at the top level, if something goes wrong in the main loop, then that's fine, that will crash. Now, let's just pretend that the author of the race detector wasn't just up here. So I don't need to say a whole lot about this, but race conditions, when you have all this concurrency, you're going to have races. And again, I said I was from Java in the past, and I've used all the concurrency stuff you can do there. And I know all these tools exist for Java, and despite that, in the 10 years I was working with Java, I never bothered to look. But it's super easy in Go because it's part of the main tool suite here. And just like we heard earlier, it'll report when a variable access is not synchronized. And when it does, it'll crash for you, and it'll show you the full stack trace, including exactly where the read and writes were. And you should use this during your unit tests for sure, but also development and integration testing. And again, here's the output. And here, this is awesome. Tracking down this type of bug would have taken forever if you're able to even catch it happening at all. And here we can see that the error happened where race.go line 14 was trying to read, while race.go line 15 was trying to write. This literally takes minutes to solve. And again, you can enable this with the -race command line option on both test, run, build, and install. OK. So this next bit isn't specific to Go, but I think it's important to address if you're trying to make a service that won't crash and that can handle some problems at runtime. Implementing timeouts. So we need to guard against some situations here. The big one is network timeouts. Now, our software, our programs are connecting to remote servers quite a bit. And for that, we dial, and then we connect, and then we transfer data, and then we're all done. Well, best practice is if you are trying to dial, you should be dialing with a timeout. And if you look at the standard library, those dial functions usually have a dial with timeouts. And so let's say it's reasonable to expect a dial to another server to take 2 seconds. Make the timeout 20 seconds. It doesn't matter. Just make it so that at some point, if there's a problem, you don't hang forever. Because if you have 20 of these connections going 100, if all day long you're trying to reach the server and it never answers, you're going to just run out of memory or have a crash. Once you have dialed, then you have to connect, and you should also have a network connection inactivity timeout. So if it's taking you, well, actually, no. In this case, a connectivity timeout is if you're transferring data back and forth, and if you haven't seen data in 10 seconds, 15 seconds, then you should just close connection and log it out. And then also, you're connected for a long time. Maybe a minute's reasonable, so timeout after 5 minutes. Timeout after a number that's ridiculous if you got that far. OK, this next one goes without saying. I'm not going to deep dive on this, but let's not skimp on the tests. Tests are super important. For me, I don't like to remember things. So after I solve a problem, I like to set up a backstop where the test has my back. And when I hand off the code to somebody else or a future me, it's still protected against these bugs. And I'll give you an example here. I'm a strong believer in integration tests. And you should look into Docker if you haven't for these kind of tests. For an example on Kiln Proxy, there's a lot going on with Mercurial and with Git when they're talking over SSH. So what I set up was an environment in a Docker container, a Docker image, which I run as a Docker container, which will actually make Git commands to a running server through my Kiln Proxy code. And so I'm trying git pull, git clone, git push, all those things. Same with Mercurial. And the nice thing about this is now maybe a new version of Git comes out, we can just have a separate instance of that container with a new version of Git, and we can have all these tests running in parallel, always making sure that our proxy is not broken. So we've just wrapped up development, and we're now starting to test out our service so we understand how it behaves. So let's start with, how does it use memory? Well, we profile it. And like probably dozens of you in the audience here, I made a profiler. This is on Fog Creek's GitHub page here if you want to take a look. It's fun to watch. I don't have an animation, but it does actually update every second. This shows me here how much memory the service is using as far as the operating system is concerned. And within that, it shows me how much is actually in use and how much the runtime is trying to give back to the system. In this case here, the purple line is memory that's ready to be freed back to the system. Sometimes the system takes it, sometimes it doesn't. So you're able to come here and see some pretty good information really quickly. The kind of things you want to watch are, how much memory does the service use when nobody's connected? This is basically your baseline. And then when you receive one connection, how much memory does that require? And then when memory ramps up and then back down, does your system reclaim your memory? Now that's going to be dependent on the system itself and the memory pressure that it's under. And then if you want to deep dive, you can take a look at what the garbage collector is actually doing by running your program with the go debug environment variable set to gctrace = 1. This is super cool to watch. And then also, you would like to know where your memory is allocated. So the memory that's in use, how did it get in use? And for that, it's PPROF. Now, I know we've seen this already at the conference, but if you guys haven't used this yet, it's going to change your life. It's super cool. And what PPROF lets you do is it lets you take a look at your service's blocking profile, the goroutine count and stack traces, and the heap profile, and stack traces that lead to thread creations. Now, this is an intimidating tool, but it's super easy to use. All you have to do is import the PPROF package, which will set up a whole bunch of HTTP endpoints for you. And then it's your job to pick the port, pick the IP, and listen and serve. Super easy to set up. And then once you do, you hit this page. And this is just the main page, but that takes you to the real meat of the output here. But right away, you already see some useful information. Like right here, we can see that we have 32 goroutines in use. And let's say this is my baseline. Let's say no users are currently connected to my local dev system. My system requires 32 goroutines. So it's important that we don't leak goroutines, as I mentioned earlier. We want to avoid these leaks because of memory leaks. And let's see. So using PPROF, we can tell how many goroutines are in use when nobody's connected. We can then connect with one user and keep that connection open and look again. And then we can, when it's all done, when you've run 100 connections or 1,000 connections, you run it overnight and everyone's done talking to your service, you should see that first number again. You should see 32 again. If you see 33, you have a problem. You should fix it. So let's say I have 33. Like, where's that extra goroutine? Well, back to that original page, you click on goroutines and you see a full stack trace. Now, we've all seen stack traces, and usually it's with great sadness. Our service crashed. Well, here you're seeing a stack trace of your service while it's running. You refresh this page, and you'll see the next snapshot of what's going on. This is awesome. You see which line each goroutine is sitting on. Now, PPROF is awesome from the web page, but where it really shines is the command line. Because you can run your command line, your PPROF command line locally. It's going to connect to these web endpoints. And it's going to, I mean, most of these endpoints are made for computer consumption anyway, so it's going to interpret this for you. So from the command line, we're going to run go tool PPROF, and then the location of the binary that's running out on the server. And then we're going to give it the HTTP endpoint to the goroutine page. And then now we're going to enter an interactive terminal. You type in top 5 to see the top 5 locations that these goroutines are waiting. You can do top 10 or top 9. It's pretty cool. And then this is fun, so if you have a problem, you're going to track that down. But then what I really like to show off is you type in web, and after you install a bunch of stuff, this works, and it pops up a browser showing you your call stack and showing you how all these goroutines came to be. This is a simple example. Once your server gets bigger, you're going to have a lot more of these boxes. This is a cool SVG graphic that you can zoom in, pan around on your browser. So you're going to track things down. You're going to find out exactly how these goroutines were spawned. And again, PPROF can help you out with your heap memory as well. And here I can see, so running go tool PPROF, the server, which is my binary, and then the location of the heap endpoint. And again, I run top 5, and I can see here, oh, looks like my biggest offender is my profiler. But then I noticed that's OK. It's only using 1.8 megabytes of my total 2.3, and that's what I expect. And you can dive down further there. And just like before, you can type in the web command, and you get your SVG opening up in a browser again. This is a super simple example. Yours will look a lot more complicated. But you see the call stack, the call trace, the call stack that shows you where this memory is being allocated. And this is great to see, because a lot of times you're using a lot of memory. You don't know why, because it seems to be out of your hands. It seems to be in a library that you're using. And so you could dive down, and maybe you can patch something. You can fix that library, or maybe just understand how it works a little bit better. So at this point, we've built our system. We've profiled it in testing, so we know how it behaves, and we've deployed it to production. So at this point, we have to be able to tell what's deployed is the first thing. So sometimes I don't trust our deployment process. Sometimes I also don't trust how we keep track of what code is in a release. So I have an endpoint that I will expose to our intranet, so it's not exposed to the outside world, called info. And I show the version. I show the start time in epoch seconds. Then I show the server's current time in epoch seconds, so that you don't have to worry about time zones. You can do some pretty complicated math to figure out how many seconds have elapsed. Or you can just look at the uptime human readable form at the end there, and I see that I have 167 hours and 10 minutes and 2 seconds, and I love seeing that number go up. So I'm going to take a brief aside to show you about this version number, because I think this is kind of a cool tip. So in this case here, the version number that I like to use is a variant. There's lots of different things you can do here. You have major, minor, release. Then you have the commit number on the tree that I deployed. And that should always go up as you deploy new code. And then you have the git SHA of the commit that was deployed, which is great because a lot of times, you tag stuff. There's a build process, but it's not you doing it, so you don't trust it. And so if I see if there's a bug, if we just launched something, someone asks, "Did you fix that bug? Is that out in production yet?" I take that SHA. I can do a git checkout, or I can just look at the git logs and find out where the fix made it. Maybe it already occurred at this point. And then at the end there, I have the date and the time of the build. And so to talk about how I am able to generate this, obviously you can't expect people to know the git SHA of the upcoming commit. That's not reasonable to expect. So what we can do here in Go is you have a global variable in your code called service version, called whatever you want. And then from the build script, from your command line, when you're building, you can set this global variable right there from the command line. So our code's already committed. The SHA already exists. And then you use the -LD flags to set main.serviceversion to that string that we build up in our bash script. And that's super useful when you're deploying 10 instances, 100 instances, thousands of instances of your service on different machines. And you can automate making sure that they're all at the right version, the same version. And so now we need to see what our service is doing. Back to monitoring what the service is actually doing. Obviously, keep good logs. We all like logs. And one little tip I can share here, and I'm sure this is not my invention. When you receive a new request, come up with a semi-random string, pass that all the way through all the functions that, or use a context or something to pass it around so that you can include that as your prefix on every log entry. Now this is super useful because when you have thousands of users connecting with concurrency, you look at your logs, it's a giant mess. You can use grep to easily find out what's going on with one connection. So next we want to know who's currently connected. Now this might not be useful for many of your services which respond within 50 milliseconds. Kiln connections, as I said, can take minutes when you're cloning a large repo. So I notice a lot of traffic, I want to see who's connected. So I have another endpoint called connections. And here I can see that I have one user. It's the Aviado account. Erlich Bachman is connected. It looks like it's his build server. People tend to name their keys build server, laptop. And he's been connected for 25 minutes and 4 seconds. So that might seem a little fishy. Maybe I've noticed some problems recently. So I'm going to take that session key, which is my log string. I'm going to go through the logs and find out exactly what's been going on throughout this session. Now, since I'm keeping track of how many users are currently connected, I can implement drain and die. I'd never thought of this. I talked to our system administrators, and they told me about this. And so what this means is when system administrators want to kill the app, kill the service because of an upgrade or just a planned restart, I'm not going to let the process end until I've served all the current connections. And so it listens for the sig term, which you can do in Go. You can listen for system events like sig term. And once I get my sig term, I stop listening for new requests. And I will just sit there and loop and sleep until all the existing requests are done. So, game day. So all this work that went into making a responsible service was put into. This is the first time it was tested. It was kind of a pretty cool day. So the system administrators got an alert from Nagios, and they said, "Blake, Kiln proxy is broken. It's using 40 megabytes more than it normally does." Now we all know that Kiln proxy wasn't broken. So let me quickly view my profiler, and not an actual screenshot, but I was able to see, yes, OK, there actually is memory usage is up there. The system is reporting what I see, and I can see that the memory is currently still in use. And so, OK, let's dive down a little bit more, and I look at my connections page, my endpoint. I can see Initech is connected 10 times. So Peter Gibbons is doing something he shouldn't be doing, or he's having a problem, or we're having a problem. And to back up a little bit, during development, I know that each connection takes about 4 megabytes of memory. And using PPROF, I know that most of that 4 megabytes was kind of out of my hands. I didn't feel like diving down any deeper, but it was mostly SSH library internals, encryption stuff. Wolfram Alpha tells me that 4 megabytes times 10 is 40 megabytes, roughly. So customer service reaches out to Initech. And yeah, sure enough, they were having a problem with their build server. I don't know, I forget. And so they stopped, they turn off the build server, restart it. We work with them, and they're happy that we noticed their problem before they did. Because I implemented timeouts, I know that all those 10 connections eventually will drain and will be closed. And because of my production profiling, I know that if the system is under memory pressure, all that extra memory it was using will be reclaimed by the system. So, uptime preserved. Now, as far as I know, I think the service it's been running for 6 months or so, and I think it's been restarted 3 or 4 times. I haven't checked Wolfram Alpha. I believe that's more than once a day. And so things worked out really well. And yeah, it was a good experience. And based on this was our first prototype, first production use of Go at Fog Creek. And it was met with a lot of skepticism. And since this has been running for so long, months at a time without being restarted, it convinced everybody there that this is a technology worth exploring. So yeah, it was a great experience for me, and I want to thank you for listening.